All right, so good day to the lecturers and fellow students. We are Group 11, and this is our presentation on the multi-threaded MD5 password cracking system. My name is Alif, and I am the team lead. For this assignment, we assigned tasks to leverage our individual strengths. For Clarence, he acted as our program runner and tester. Brandon developed the course search space and algorithm. Xavier engineered the multi-threading architecture, and Mingzin managed the development support and the documentation for this assignment. Okay, so our presentation is divided into three technical sections. The first is the implementation logic of our password cracker. The second is synchronization method used for thread safety. And lastly, the execution and result, including live demonstration. Our goal is to solve the computation intensive problem of checking over 700 billion combination for a 6-character password by leveraging Java concurrency libraries.
So I will start with the part one, implementation logic. So our setup process has actually have four steps. First, we validate the inputs, which is ensuring the hash is correct. And then second, we apply the thread configurations. So we're limiting the user to between 1 to 10 threads. And then this third is task submissions, where we divide the workload. And then finally, we initialize the reported threads to track our real-time progress. So for multi-threaded brute force approach, our architecture relies on four pillars. Firstly, we use a brute force strategy to systematically test every combinations, and then we implementing the multi-threading to split this massive search space across multiple cores. Also, that we apply performance optimizations like thread local and the batch updates to maximize speed. And plus, we use real-time monitoring to provide live updates on hash rates and completion time. So moving to the search space topology, we utilize the 95 printable ASCII character ranging from decimal 32 to 36. And then we actually target the password length from 2 to 6. So crucially, we like pre-calculate the total combination using the summation formula shown here. And this calculation is vital for progress tracking and allowing us to accurately estimate the remaining time against the 700 billions total possibilities.
I will explain how we parallelize the search using a three-step strategy. First, our parallelization strategy utilizes a fixed thread pool, allowing us to manage the user-specified thread count effectively. Second is workload partitioning. To ensure fairness, we calculate a base chance to distribute the 95 access character evenly among the thread based on the first character of the password. Third is independent execution. As shown in the bottom snippet, each thread runs an isolate loop for its assigned range, checking all password lengths from 2 to 6 without interfering with other threads. I will now explain the core algorithm. We use an interactive automated approach. This is a flat loop structure which is crucial because it avoids the heavy memory overhead of recursion. For length 2 handling, we use a simple nested loop strategy. This is extremely lightweight and lets us rapidly check all two characters combination without complex logic. For length 3 to 6, we use an integer array method shown here. We maintain an array of integers that acts like a cast automator. We increment the last digit, and if it rolls over the limit of 95, we reset it and carry over to the next position. This allows us to generate millions of passwords per second systematically, ensuring no combination is even skipped or repeated.
To achieve high throughput, we implemented critical performance enhancements. First is thread local optimizations. So standard MD5 instantiation in Java is synchronized and slow. By using thread local, we give every single thread its own private MD5 instance. This completely bypasses the synchronization bottlenecks in the Java security provider, allowing all threads to hash in parallel at maximum speed. Our second optimization is the use of byte arrays. In Java, creating a string object is memory heavy. Since we test millions of combinations, we use raw byte arrays to hold the candidate passwords. We only pay the cost of converting bytes to a string at the very end. Once the correct password has been found, this significantly reduces the load on the Java garbage collector. The third and most impactful optimizations is batch atomic updates. Updating the local progress counter after every single guess would cause massive thread contention, where threads fight for memory access. Instead, we use a local counter within each thread. We only synchronize with the global atomic long once every 10,000 iterations. This reduces locking overhead by 99.99%.
So, moving to the atomic boolean is found in section 2 about synchronizations. So, our primary control mechanism is the global Q switch. It's implemented via an atomic boolean name is found. So, unlike a standard booleans which can be cached by CPUs, the atomic booleans guarantees that the change are instantly visible to all threads. So, like as shown as in the code, every thread check is found gets in its loop. So, the moment is a thread find the password, you use compare and set to flip the flag to true. So this triggers an immediate response, forcing all other threads to stop work instantly and preventing them waste resource.
To store the final result, we utilize an atomic reference. This provides thread-safe password storage, ensuring that if multiple threads discover the password simultaneously, the update is handled cleanly without rest condition. It allows for lock-free atomic operation, meaning other threads can safely check the status without being blocked, ensuring high concurrency throughout the search.
For progress tracking, we rely on an atomic long counter. To achieve safe concurrent updates without performance loss, we implement a batch update strategy. Threads count locally and only synchronize with this global atomic counter every 10,000 iterations. This drastically reduces memory contention while still providing data for real-time monitoring by the reporter thread.
Moving on to the execution phase, to monitor our progress without slowing down the system, we implemented a dedicated reporter thread. As you can see here, we designed the thread to be decoupled, meaning it runs purely in the background. This ensures that printing updates to the screen never blocks the critical worker threads. We also used interval polling thread.sleep 1000 to update the status exactly once every second. The code also includes a safe termination check. It constantly monitors the is found flag so it stops immediately when the password is discovered. I will now explain the maths behind our monitoring. First, we calculate the real-time hash rate by dividing the total combination tried by the elapsed seconds. Second, we derive the progress percentage to show exactly how much of the search space has been covered. Third, we provide a dynamic ETA. By dividing the remaining workload by our current speed, we generate a precise countdown in hours, minutes, and seconds, which adjusts automatically to system load. Moving to section 3, instruction of execution and result, I will talk about how to execute the program first. Executing the application is very straightforward. First, you have to ensure you have Java JDK 8 or higher installed. Step 1 is to compile the code using the command java c filename. In this case, it's md5cracker.java. Step 2 is to run it using java md5 cracker, passing in the target md5 hash and the desired thread count as arguments. The system automatically validates this input to prevent runtime errors. Here is the output from a successful run. At the top, you see the initialization data and the real-time progress updates, including the hash rate and ETA. Upon finding the password, the system generates a comprehensive report. It displays the thread ID, the recovered password, the exact position in the search space, and the total time spent and any other relevant info. This confirms that our threading and reporting logic are working correctly. Now, I will play a short demonstration video showing the application running in real time from compilation to successful finding a password. Here is a live run of our application. While our full performance analysis tests 1, 2, 4, 6, 8, and 10 threads, this demo highlights specific examples. First, we run the 3-character password search. As you can see, it completes almost instantly for all thread counts. Immediately following that, we test a 4-character password. Aside from the single thread execution which takes a moment, increasing the load to more than one thread like 2, 4, 6, 8, and 10 threads count allow the search to finish almost instantly as well, just like the 3-character password search.
Now let's analyze our performance data. Here we have the result of 2 and 3 character password. You might expect the graph to drop as we add threads, but as you can see, the line stays relatively flat or even rises slightly. This is because the result is effectively instantaneous, taking only fraction of a second. For such tiny workload, the overhead of creating and managing multiple threads is actually higher than the time saved by parallelization. Therefore, adding threads here does not improve performance. Moving to the heavier workload of 4, 5, and 6 characters, the benefits of parallelization becomes undeniable. As you can see in all of the graphs, the search time dropped drastically as we move from 1 threads to 4 threads. For 6 character password, we reduced the time from nearly 8 hours just down to under an hour. However, you will notice sharp spikes, for instance, at 3 threads or 7 threads. This is due to uneven search space distribution. Since we divide work by the first character, a thread might get a chunk where the password is at the very end of its list, causing it to run longer than the others. Despite this variance, the overall trend confirms that multi-threading is essential for this longer length. In this final summary, we plotted all password lengths on a single logarithmic scale to visualize the difference. You can clearly see that the trivial password, the bottom blue and the orange lines, threading makes almost no difference. However, the complex 6 character password, the purple line at the top, the impact is dramatic. We see massive drop in search time, specifically between 1 and 4 threads. This proves that our system is correctly architected. It remains lightweight for simple tasks but scales up its processing power aggressively when faced with a heavy cryptographic challenges. That concludes our presentation. On behalf of Group 11, thank you for listening.